Welcome to section 11.2. This is a section in which we're going to find a different way to solve systems of equations using what in this term is a matrix. So we're going to be solving systems of equations using matrices. And so I'll give you a general overview right here, especially if this is the first time that you've ever done something like this. It literally could be, but it's not expected that somebody would see this before, but often in an intermediate algebra class, especially a high school class, they might have had the time to go over solving equations by what they call an augmented matrix. And so I'll give you the layout here. I want to definitely put something into your mind early, and that is you're going to watch different ways to solve systems of equations happen. There's going to be this way by using matrices, and 11.3 we'll do it by what's called Cramer's rule using determinants. And you could get a little bit frustrated because you can realize that, hey, if I would just use substitution or elimination, it'd be really faster. The only reason that is because they're giving you nice examples. And so be careful. The reason why this is being taught is to have you solve more efficiently some where the answers just don't come out very quickly through a substitution or elimination process. And so the goal is to just expose you to a whole bunch of forms of solving systems of equations, because the reality is we're going to have to use them because our systems are just too big in the future, or the numbers are just too crazy, and it would be better to organize them in these types of ways. So that's my little disclaimer for how you're going to feel sometimes, like, why am I doing this? And it really is just for exposure. And so the way an augmented matrix works is you'll be given a system of equations, and I just took some time to type one out there. And what it does is a matrix realizes it's very similar to synthetic division. It realizes that all I have to do is keep track of x's, y's, and z's, and as long as I know where they are, then I will definitely be able to find them. So what I mean by that is we're not going to write all those variables. A matrix typically has a little bracketed off notation, and what we're going to do is just write the coefficients of the x, y, and z term in the first, second, and third column respectively. So we're going to know that x is always that first column, y is always the second, and z is always the third. Now they're going to refer to it as an augmented matrix because it has this augmented side, and we put the constant over there. So it's important that x, y, and z are on one side and the numbers on the other. I don't think they're looking to trick you in the book, but we'd want all your variables on one side for this thing to work. So over here we're going to have in the next row it's 5, 6, 7, 8. And then the last row it's 9, 10, 11, 12. So that's how you create your augmented matrix. And so what we're going to do is work with that thing and get it so that you can just read the answers. And the way that we work with it is by using row operations. And so I copied this from the book. It's pretty standard. But the things that you're allowed to do is you're allowed to change any two rows. You can move their positions however you want. Just like it didn't matter up here what order I put these equations in, it wouldn't necessarily matter if the 9, 10, oops, I forgot that I have my eraser still. It wouldn't matter if we took this 9, 10, 11, 12 row and moved it up to the top if we felt that that was more advantageous. Now, you're going to wonder, well, why would you want to do that? Well, there's a goal in mind, but you can definitely interchange any two rows as long as you feel like it's helping you get to the end answer. That's an okay thing to do. The other thing that you're allowed to do is replace any row by a non-zero multiple of that row. So you can multiply it by anything you want and divide it by anything you want. And as long as you don't multiply or divide by 0, you're going to be fine. And then you can also replace a row by the sum of that row and any other non-zero row. And you'll see this happen as we work through examples. The whole goal in doing these row operations is to be able to get you to see the answer. And so the goal is to get ones along the main diagonal with zeros underneath. And so ultimately, let me switch back to black because I think that would be easier. Ultimately, what you want to see is something like this. I'll put anything here, 1, 0. Anything here, and a 1. That's what you'd like to have. and you'd have some kind of number here, and number here. When you get it to a situation like this, you can easily start uncovering the answer, because what you're going to know is that, remember what this is saying, this last one is saying z is equal to a number. It's saying 1 times z is equal to a number. So you'll know what z is. Knowing what z is, you can plug it into this equation and figure out what y is. And knowing what y and z are, you can plug them into the first and figure out what x is. The other thing that this will do sometimes, it will definitely show us when we have a whole bunch of solutions or no solutions. So if you were getting it into, sorry, this could be anything up here. Anything. Let's suppose we were doing this process and we got a 0 here, not a 1, and a 0 here. This would mean that there's a bunch of solutions, right? This is what it looks like when you have an infinite number of solutions. And we would describe them that way. In fact, it's pretty easy to describe them that way. We'll basically be able to say z can be anything and then relate y and x to z, and it will work out really, really nicely. The other thing that could happen is you go to do it and you get 1, 0, 0, anything, 1, 0, and anything, 0, 0. And you can think, well, that's infinite too. Not when this happens. So this can be anything, this could be anything, and let's suppose this is a number like 4. Now up here, when we had a bunch of solutions, sorry about doing that so close, we had the true equation out of here. Let me redo what I circled. We have the true equation that 0 equals 0. Look at what that last line says. It says nothing is equal to nothing. And that's true. That's why we had a bunch of solutions. But what is this saying? It's saying nothing is equal to 4. Well, that's not true. So this is the inconsistent, right? That's the word that they use in our book. Inconsistent system. This is the no solution system, because there's just no way that they coincide, because we would need 0 to be equal to 4, and it's not. So that's why we use matrices. It's just another way to do it. I'll show you some examples, but we're going to do these row operations to ideally end up with something like this and just name that answer.